Imagine two men waking up on the same morning. They slept the same number of hours, ate roughly the same amount of calories the day before, and even go to the same gym. But when they get out of bed, their bodies feel completely different. One feels sharp, driven, and physically powerful. His mind feels focused, his energy feels stable, and he moves through the day with a sense of momentum. The other feels slow, foggy, and strangely drained before the day has even started. His motivation is inconsistent, his concentration fades quickly, and by early afternoon he is already searching for caffeine or sugar just to stay functional. On paper, their lifestyles may look similar, but biologically, their internal environments are operating very differently. And one of the hidden factors that can shape that difference is the way the body regulates hormones, particularly testosterone. Testosterone is often discussed in simple terms, usually in connection with muscle growth or athletic performance, but its role inside the human body is far more complex than that. Testosterone influences energy levels, motivation, mood regulation, cognitive focus, body composition, bone density, and even risk-taking behavior. In many ways, it functions as one of the central chemical signals that help regulate how energized and resilient the male body feels on a daily basis. But testosterone production does not exist in isolation. It is part of a larger hormonal communication network known as the hypothalamic-pituitary-gonadal axis. This system begins in the brain, where the hypothalamus sends signals to the pituitary gland. The pituitary then releases hormones that travel through the bloodstream to the testes, instructing them how much testosterone to produce. When this communication network functions smoothly, hormone production tends to remain stable. But when signals inside this network become disrupted, testosterone regulation can shift in subtle ways that affect energy, performance, and long-term metabolic health. One of the most powerful influences on this hormonal signaling system is not a supplement, a workout program, or a medication. It is metabolism. More specifically, it is the metabolic signals created by the presence or absence of food. Every time you eat, a complex cascade of hormonal responses begins inside the body. Nutrients enter the bloodstream, insulin rises to help move glucose into cells, and the body enters what scientists call the fed state. In this state, the body prioritizes digestion, nutrient storage, and energy distribution. Insulin plays a central role in coordinating these processes, acting almost like a traffic controller for incoming fuel. Without insulin, the body could not regulate blood sugar or properly store energy. However, problems begin to appear when the fed state becomes almost constant. In modern eating patterns, many people consume food from early morning until late evening: breakfast, coffee, drinks, snacks, lunch, more snacks, dinner, and sometimes another snack before bed. When this happens, insulin levels may remain elevated for much of the day, leaving very little time for the body to enter the opposite metabolic condition, the fasting state. From an evolutionary perspective, the human body did not develop in an environment where food arrived every few hours. For most of human history, meals were irregular and often separated by long periods without food. During those fasting periods, insulin levels naturally dropped and the body shifted toward using stored energy. This metabolic rhythm, alternating between feeding and fasting, allowed the body to move between different fuel systems depending on environmental conditions. When food was available, the body stored nutrients and built tissue. When food was scarce, the body mobilized, stored energy, and maintained survival systems. This rhythm was not simply about burning calories. It also influenced hormonal communication throughout the body. Testosterone production, for example, is sensitive to the broader metabolic environment. Hormonal signals that regulate reproduction and tissue growth are closely linked to the body's perception of energy availability. If the body interprets its environment as metabolically stable and efficient, those signals tend to remain balanced. But if the metabolic environment becomes chronically stressed, hormonal regulation may begin to shift. One of the interesting questions researchers have explored over the past 2 decades is how intermittent fasting might influence this metabolic environment. Intermittent fasting is often misunderstood as simply a form of calorie restriction, but in reality it is more accurately described as a pattern of meal timing. Instead of eating continuously throughout the day, individuals create defined periods without food, commonly 14 hours, 16 hours, or sometimes longer. During these fasting windows, insulin levels decline, fat metabolism gradually increases, and the body begins transitioning towards stored energy usage. But the most important change may not be fuel selection alone. The deeper change involves the hormonal signals that respond to that metabolic shift. However, this transition does not always feel smooth in the beginning. Many people who start intermittent fasting experience a period of adjustment during the first several days. Energy may feel unstable, workouts may feel more difficult, and some individuals notice temporary changes in mood or libido. Without understanding the biology behind this process, it is easy to assume that something is going wrong. In reality, the body is often going through a temporary adaptation phase. When eating patterns change suddenly, the nervous system initially interprets the reduced food frequency as a potential stress signal. From an evolutionary standpoint, this makes sense. For most of human history, a sudden reduction in food availability could signal environmental scarcity. In response, the body activates short-term survival pathways designed to increase alertness and maintain energy supply. One of the hormones involved in this process is cortisol. Cortisol helps mobilize stored energy and maintain blood glucose levels when food intake decreases. However, cortisol also interacts with testosterone in complex ways. These two hormones often behave like opposite ends of a biological seesaw. When cortisol rises sharply, testosterone production can temporarily decrease. This relationship has been observed in several physiological studies examining short-term fasting and stress responses. Importantly, this temporary shift does not necessarily represent long-term hormonal decline. Instead, it reflects the body adjusting to a new metabolic rhythm. Understanding this early adaptation stage is essential because many people stop fasting during precisely the phase when the body is still recalibrating its internal systems. Once the body begins adapting to a new metabolic rhythm, something interesting starts to happen inside the nervous system. After several days of intermittent fasting, the brain gradually shifts the way it manages energy and alertness. Instead of depending entirely on frequent glucose intake from food, the body begins mobilizing stored energy more efficiently. At the same time, certain neurotransmitters begin to rise, particularly norepinephrine and dopamine. Norepinephrine increases alertness and reaction speed, while dopamine plays a major role in motivation, reward, and goal-directed behavior. From an evolutionary perspective, this makes perfect sense. In an environment where food was scarce, becoming sluggish or mentally foggy would have reduced the chances of survival. Instead, the human brain evolved to become more alert when food availability temporarily dropped. This shift often produces a mental state that many people describe as increased clarity or focus. It is not a stimulant-type energy spike like caffeine, but rather a steady sense of alertness that persists for longer periods. During this stage, the body is also becoming better at switching fuel sources. Early in the fasting transition, the body still relies heavily on glucose stored as glycogen in the liver and muscles. But as fasting continues, glycogen stores gradually decline and the body increases its reliance on fat metabolism. Fatty acids begin circulating in the bloodstream and are converted into alternative energy molecules that tissues can use. This process does not simply provide energy. It also changes the hormonal environment in which other biological systems operate. When insulin levels remain lower for extended periods, the body is no longer constantly receiving the signal to store energy. Instead, it begins prioritizing energy release and metabolic efficiency. These shifts may influence how other hormones interact with cells, including hormones involved in reproduction and tissue growth. One of the most misunderstood aspects of testosterone biology is the assumption that higher hormone levels automatically lead to stronger biological effects. In reality, hormones function more like signals in a communication network. The strength of that signal depends not only on how much hormone is present, but also on how responsive the receiving cells are. In the case of testosterone, this responsiveness is controlled by structures known as androgen receptors. These receptors sit on the surface of cells throughout the body, particularly in muscle tissue and parts of the nervous system. When testosterone binds to these receptors, it activates a series of biological processes related to muscle development, motivation, metabolic regulation, and physical performance. However, receptor sensitivity can change depending on metabolic conditions. Chronic metabolic stress, inflammation, and constantly elevated insulin levels may reduce how responsive these receptors become over time. Some researchers have suggested that improving metabolic health may help restore the responsiveness of these receptors, allowing normal testosterone levels to produce stronger biological effects. This concept helps explain an observation often reported by individuals who practice intermittent fasting long-term. Even when blood tests show only modest changes in testosterone levels, many people report improvements in energy stability, motivation, and physical performance. This does not necessarily mean that fasting dramatically increases testosterone production. Instead, it may reflect improved hormonal efficiency. When the metabolic environment becomes more stable and cells become more responsive to hormonal signals, the same amount of hormone can generate stronger effects. In other words, the body may not need to produce dramatically higher testosterone levels if the existing hormone signals are being used more effectively. Another hormone that becomes particularly interesting during fasting is growth hormone. Growth hormone is released by the pituitary gland and plays an important role in maintaining lean tissue, repairing cells, and regulating metabolism. Research has shown that fasting periods can stimulate increases in growth hormone secretion. The biological reason behind this increase is related to energy management. When the body detects a reduction in incoming calories, it activates protective mechanisms designed to preserve essential tissues while mobilizing stored energy. Growth hormone helps coordinate this response by encouraging fat breakdown while helping protect lean muscle mass. This combination can be especially important during periods when energy intake is temporarily reduced. Rather than immediately breaking down muscle tissue, the body shifts toward using stored fat as fuel while maintaining critical structures. Body fat itself also plays a role in hormonal balance. Fat tissue is not simply passive storage for excess calories. It is metabolically active and contains enzymes that influence hormone conversion. One enzyme of particular interest is aromatase. Aromatase converts testosterone into estrogen, a process that occurs naturally in both men and women. However, higher levels of body fat can increase aromatase activity. This means that individuals carrying more visceral fat may experience greater conversion of testosterone into estrogen. Over time, this shift can influence the overall hormonal balance in the body. When individuals reduce excess body fat through improved metabolic health, aromatase activity may decline, helping maintain a more balanced hormonal profile. This does not necessarily mean testosterone levels increase dramatically, but it may help preserve healthier ratios between different hormones. Another biological process often discussed in fasting research is autophagy. Autophagy literally translates to self-eating, but the term can be misleading if interpreted incorrectly. The process does not involve the body randomly destroying healthy tissue. Instead, autophagy functions more like a cellular recycling system. When nutrient intake temporarily decreases, cells begin breaking down damaged proteins, dysfunctional components, and other forms of cellular debris. These materials can then be reused to build new cellular structures. In simple terms, fasting may provide cells with time to perform maintenance that is less active during constant feeding. This process has been studied extensively in cellular biology and has been associated with metabolic health and longevity research. Importantly, short periods of fasting do not automatically cause muscle loss. The body tends to prioritize preserving functional lean tissue, particularly when overall nutrition and resistance training are maintained. Early changes in body weight during fasting are often related to reductions in glycogen and the water stored alongside it rather than actual muscle loss. As metabolic flexibility improves, the body becomes more efficient at switching between fuel sources without needing to break down critical tissue. Ultimately, the long-term benefit associated with intermittent fasting is something researchers call metabolic flexibility. Metabolic flexibility refers to the body's ability to transition smoothly between burning carbohydrates and burning fat depending on energy availability. In metabolically inflexible states, often associated with chronic overeating and insulin resistance, the body becomes less efficient at switching between these fuel sources. Energy fluctuations become more dramatic and hunger signals become more intense. By introducing regular fasting periods, the body may gradually restore its ability to move between different metabolic states more efficiently. Instead of remaining locked in a constant fed state, the body regains the natural rhythm of feeding and fasting that shaped human physiology throughout evolution. Understanding this broader perspective helps clarify an important point. Intermittent fasting is not a magic switch that instantly boosts testosterone. Rather, it influences the metabolic environment in which hormones operate. When metabolic health improves, hormonal communication may also become more stable and efficient. Over time, this can support energy balance, body composition, and overall physiological resilience. Of course, fasting is not appropriate for everyone, and individual responses vary depending on lifestyle, health status, and nutritional habits. But the growing body of research suggests that meal timing may influence far more aspects of physiology than previously understood. If there is one takeaway from this discussion, it is that the body is not designed to operate in a constant cycle of feeding. Periods of rest from digestion may allow important regulatory systems to recalibrate. Hormones, metabolism, and cellular repair processes are deeply interconnected, and small changes in daily patterns can influence how these systems function over time. Understanding these biological rhythms does not require extreme interventions, but it does require recognizing that human physiology evolved under very different conditions than those of the modern food environment. If you found this explanation helpful and want to explore more science behind everyday health decisions, consider subscribing to Real Life Body Science. Our goal is to break down complex biological systems into clear explanations so you can better understand how your body actually works.